Welcome to the first true video lecture on electric circuits. Throughout this one here, we will look at a lot of the basic stuff and kind of review that and just put definitions to terms and go through that. Whereas later on, we ramp up the difficulty pretty quickly once we cover the basic topics. So be prepared and make sure you understand this. This covers sections 20.1 to 20.4 in your textbook. We've already talked about voltage and in the idea that it's the electric potential difference between two places. Now, when there is an electric potential difference, this creates what's called an electromotive force, or an EMF. We'll talk about this EMF more when we come into magnetism later on. But for right now, this EMF creates a force that causes charge to flow. And when we have this, it creates an electric field out there, which causes electric charge to move. How this works when it refers to a battery and the voltage of a battery is that there is a potential difference created between 2 points, and it causes charges to move. And within something of very small resistance, like a wire or something like that, the charges will move through in order to kind of equal out that potential difference. The voltage of the battery is what's providing that energy per charge. So when you see like a 9-volt battery, it's providing 9 joules per every coulomb of charge that it gets. 9 volts is 9 joules per coulomb. So this is it's a energy per charge rating. The EMF force is something we'll come back to a little bit more, and it's just an older term, not as important right now. But the big idea, voltage is providing the energy per charge and causing the charges to move, creating that potential difference. Here on the bottom right, I have an example of a pile battery, which is just stacks of individual little mini potential differences, and that's how a lot of some batteries are created this way. When there's a difference between the electric potential between 2 points, or a voltage, there's created an electric field. So within a wire connected to a battery, there's an electric field created. This electric field pushes a force on free electrons, causing them to move. This movement of electrons is known as electric current. So within this way, the electric current is the flow of charge. It's the flow of electric charge, and we'll talk about the units in a second. Now, historically, it was thought that the positive charges within a substance were the ones that were free to move around. So we measured current Current is measured going from positive to negative. So it's measured as the flow from positive to negative. Whereas what actually happens is the electrons flow from negative to the positive side on a battery or on from a potential difference. So once again, current, flow of electric charge, we measure it from positive to negative. It's actually the flow of electrons moving from the negative side to the positive side. All right, current. Current is measured in coulombs per second. It is the charge flowing per second. A coulomb per second is equal to an ampere. So we have current. It's how much charge passes at a given point in a certain amount of time. Pretty straightforward. Coulomb per second and ampere. And the symbol for current, this is a little weird, is I, not C. C was used too much, so it's current is the symbol that we use is I. Here's a little graphic organizer to help you look at and understand all the different symbols and units that we're going to talk about. I'll go into resistance in a little bit more in depth in a second, but this is just something to help you organize the different things. So here it is, and it can begin now. All right, Ohm's law is the relationship between voltage, current, and resistance. This is traditionally how it's written. V is equal to I times R. I like to write it as current is equal to voltage divided by resistance. So current and voltage are directly related, whereas resistance and current are inversely related. So if you increase the voltage, the current will increase. If you increase the resistance, the current will decrease. So this is within a circuit. So we'll come back to using this to find voltage drop and current through and resistance, etc. But this is just going to be the main equation that we're going to use, Ohm's law right here. Resistance really is the ability of something to convert electrical energy into other forms. Another way that we look at it is how much something resists the flow of current. That's not entirely correct within a definition, but it is kind of this obstruction to the flow of current through an object. Something with a high resistance will prevent current from flowing just because it takes more energy. It converts more of that energy out, so there's less potential difference between something. It's kind of a bad definition. There's no real good definition out there for it. But resistance is measured in ohms. That's that little, it's a Greek letter ohm. It kind of looks like a horseshoe. It's omega. It's a capital omega. And next we have resistance here. The resistance depends on, for a wire or something like that, or for certain material, depends on the length of the material, the area, cross-sectional area, and what's called the resistivity. This is just a constant for different types of materials. So if you look here, you have copper and aluminum and gold are all very good conductors. They have a very low amount of resistivity, whereas rubber is almost 10 to the 23rd times greater more resistance than those three metals. So rubber will resist the flow of electric charge very well. Power is the rate that work is done. When we talk about electrical power, it's the rate that electrical energy is converted into other forms. So power is measured in a watt, which is a joule per second. So if we do out the units here, power is equal to current times voltage. Current is measured in coulombs per second. Voltage is in joules per second. The coulombs cancel out, so you have power is joules per second. You can always use Ohm's law to substitute in here for, say, that power is equal to, for example, the voltage squared over the resistance, if you combine this equation and the Ohm's law equation. So here's kind of a sample calculation here. How much power will of current, will a current of 5 amps across a potential difference of 10 volts draw? Calculate it out. Boom, you're left with 50 watts. So pretty straightforward calculations. I believe you've seen some of this stuff perhaps before, but we'll be moving on. All right, thank you very much. Couple questions here to sum up the video and just kind of review stuff. First, I'd like you to describe how current flows in a circuit. Second, I'd like you to give the unit for each of the following quantities. So resistance, power, current, and voltage. And then two problems. One, a toaster has a resistance of 35 ohms. If it is plugged into a wall, 120 volts or thereabouts, somewhere around there, maybe 115, but we'll use 120. What is the power used by the toaster? This is going to take two steps. You're going to need to use Ohm's law and the power formula. Second, calculate the internal resistance of a 7-meter long copper wire that has a diameter of 2.05 millimeters. So I want to know the internal resistance of copper wire with a diameter of 2.05 millimeters. That's millimeters. Thank you very much. Make sure to answer these questions online, and I will see you in class tomorrow.